Today's topic is vector functions of a scalar variable. As the name suggests, a vector function of a scalar variable is a function that takes a scalar as an input and returns a vector as an output. F of t equals to an n tuple, f1 of t, f2 of t, all the way to fn of t. Where each component, f1, f2, and fn, are scalar functions, are scalar valued functions. So these are your familiar functions from Calc 1 and 2, like sine, exponential, and whatnot. We often interpret such functions as parametric curves with the scalar argument as a parameter. The way it works is that you can imagine there is a particle moving in space. So imagine at time t1, the position is at rt1. And at another instance, at time t2, the position is at rt2. And then you can imagine if I trace out the trajectory of the particle at any time instance, at all time instance, they'll form a curve. All these positions will form a curve. And the difference between a parametric curve and just a regular purely geometric curve is that a parametric curve always carries a direction. So let's imagine, let's say T1 and T2 are in this order relation. So T1 is less than T2. Then in our diagram, you will have an arrow pointing from RT1 to RT2. And of course, the scalar does not have to be time. It can be arc length, for example, and also angle, etc. So now let's look at a specific example. We can take the angle, so to say, as indicated here as the parameter. You pick an arbitrary point on the circle and you connect that point to the origin. So this forms a radius, a radial vector, basically, the radial vector. And so the radial vector and the positive x-axis form an angle, and that is our parameter. So in this case, you would have x equals to r cosine of t, cosine of theta, and y equals to r sine of theta. Just from some basic trig relations. And we can write that as a vector function, RT. Usually we use R as the displacement, the position vector notation. RT is a notation for the position vector. So RT is xt, yt. Actually, I should use theta here. I'll get to t later. So here the parameter is theta. So r theta equals x theta y theta equals to r cosine theta r sine theta. So this is one parameterization where we use the angle as the parameter, or we can assume that this circle is the trajectory of a particle moving in a circular motion with angular velocity omega, angular speed, in fact. So that means theta is proportional to time. T is time. So theta increases linearly with respect to time. So now, of course, you can rewrite your position vector r as a function of t. So rt is r cosine of omega t, r sine of omega t. So you just replace theta by omega t. And also, last but not least, we can use the arc length. By that, I mean the length of this highlighted portion of the arc. So S is the arc length from R0 to XY. This gives us a relationship S equals to R times theta. So you can even write your vector function whose parameter is the arc length, Rs. Rs equals to R times the cosine. Now theta is just S divided by R. So this is cosine of S divided by R. And the second component, of course, is R times the sine of S divided by R. You can see, given a curve, the parameterization is not unique. Okay, so now we know what a vector function is. We can introduce calculus of vector function, namely the derivatives and integrals of vector valued functions. Because we have all these components being scalar functions, all you need to do is just to take the derivative or integral of each component. And that will give you the derivative or integral of the vector value function. as a whole. So let's write that. So this is a fairly simple operation, but it has a nice geometric meaning. Because recall, what is the definition of a scalar derivative? The scalar derivative is the instantaneous rate of change. And that meaning gets carried over to vector functions as well. So imagine we have this vector valued function visualized as a parameterized curve. And let's say this is t. And here we have the location RT. And let's say at some next instance, t plus delta t, the particle moved. The difference between RT and RT plus delta t, according to vector algebra, is just this increment vector. So R prime of t is just the limit of delta R over delta t, where delta R equals to RT plus delta t minus RT. Delta t goes to 0. So as you can see, because from the picture, delta R is a secant line segment of the curve. When t goes to infinity, delta R becomes infinitesimal displacement. This ratio becomes a vector tangent to the curve. So this is a tangent vector. And this brings us to the physical application of the derivative. Imagine RT as a displacement function. This tells you the exact position of a particle at an arbitrary time instance t. We often write this in mechanics. So d over dt is just often abbreviated as a dot. Okay, let's say you have some quantity dA over dt, and you just write a dot. This is just a common notation in mechanics. Whenever you're differentiating with respect to time, you can just put one dot above. If you're taking second order derivative, you put two dots on top. So the velocity, v, is r dot. And acceleration is the second order derivative. I put double dot here. And you might even heard of this quantity called jerk, useful in ergonomics, j, defined as a third order derivative. The speed is the length of the velocity. You just take the Euclidean length of the velocity. These basic notions, such as length, were reviewed in the previous video called vector algebra. And the integral, of course, is the reverse operation. The integral of f of t dt is nothing but the integral of the component. And I'm writing this as an indefinite integral. You can, of course, replace the indefinite integral by a definite integral, as long as all the integration limits are the same. Now let's look at a real life problem. So this has to do with this parking garage. And as you can see, there's this spiral ramp built next to it, right, in order to access various storage of the parking garage. Let's consider a multi-storage parking garage, see the picture above, with a floor-to-floor height of 3.6 meters. The ramp is called a circular helix. The circular helix has a radius of 8 meters. So that means if you imagine seeing this ramp from a top-down view, you will just see a circle. And that circle would have a radius of 8 meters. Research shows that the maximum acceleration that a passenger would feel comfortable is around 2.16 meters per second. So given these data, we would like to calculate the recommended speed limit on the ramp, as well as the time needed to drive from the ground level to the top level. So I've drawn some schematics to illustrate the essential part of this problem. So here's a 3D view of the circular helix in one revolution. Okay, and this is the top-down view I was talking about, it's just a circle. So first, we need to find a parameterization of the circular helix. So because the projection on the xy plane of the helix is just a circle, so that's the radius r. So x equals to r cosine of theta. Once again, I'm picking an arbitrary point on the circle, connected to the origin, and use the angle between the position vector on the xy plane and the x-axis to be our parameter. X equals to r cosine theta, y equals to r sine theta. What about z? The fact that the curve is a helix implies that z has to increase linearly with respect to the angular variable. That's just follows from the definition of helix. So z is some constant k that I don't know of times theta. we can actually use the geometric parameters given the problem to figure out k. Because since after one revolution, that means theta goes from 0 to 2 pi, z goes from 0 to h, the height of one storage. So we have h equals to k times 2 pi. And as a result, k can be solved to be h over 2 pi. So therefore, now we have a parameterization r of theta. The parameterization of the circular helix, r of theta. So this is r cosine theta, r sine theta, h over 2 pi times theta. We need to derive the velocity, speed, and acceleration from this parameterization. V, which is r dot. Bear in mind, r dot is defined to be a dr over dt. T is time. However, our r is not parameterized by time, right? So therefore, we need to use a chain rule. So dr d theta times theta dot. We're going to plug in the expression here. So dr d theta, we're just going to differentiate each term. So here we have r times minus sine of theta, comma, r times the cosine of theta, and h over 2 pi. This is dr d theta, and then multiplied by the scalar theta dot. This is the velocity. And the speed is the velocity length. That gives us the square root of r squared sine theta squared plus r squared cosine theta squared plus h squared over 4 pi squared. You use the familiar identity, this simplifies to r squared plus h squared over 4 pi squared theta dot. Here is an interesting observation. Suppose that the speed is constant. Right now, we don't know what the speed is, right? We wish to calculate that in part A, but let's just suppose that is a constant. We would have theta dot being a constant as well, because theta dot can be rearranged into v length over the square root of r squared plus h squared over 4 pi squared. On the denominator is also a constant, so therefore this is a constant. Theta dot is a constant in our scenario. What about acceleration? We're also given information regarding the acceleration, so we might as well calculate that. So the acceleration A is v dot. So we need to use chain rule once again, dv d theta, and then times theta dot. So that gives us minus r cosine of theta minus r sine of theta. And the last component of v is just a constant. So taking derivative will give us 0 times theta dot. And because v already comes with a theta dot, so now you have to times another theta dot, so that gives us theta dot squared. So this is acceleration. And the information regarding the acceleration says this. The research shows that the maximum acceleration that the passenger feel comfortable is around 2.16 meters per second squared. So this must refers to the magnitude of the acceleration. So therefore, let's take the magnitude of the acceleration. That gives us, well, this is just r squared cosine squared theta plus r squared sine squared of theta. The 0 component does nothing, the theta squared. So this just r theta dot squared. These are the basic quantities that we derived from our parameterization. So now let's look at part A. So since A maximum, this is 2.16 meters per second squared. We can use the relationship between A and r dot, and also r dot and v, to solve for the maximum speed. A length is equal to r times theta dot squared. Well, this is our theta dot, so theta dot squared, which is going to be a v length squared over r squared plus h squared over 4 pi squared. So v length can be solved as such: a length times r plus h squared over 4 pi squared times r, and then taking the square root. So therefore, Vm would be AM times R plus H squared over 4 pi squared R, taking the square root. So now we can plug in the data and simplify. And this simplifies to 4.17 meters per second, which is 15 kilometers per hour. So that's the recommended speed limit on the ramp. The time it takes to drive from the bottom floor to the top floor. One method is to calculate the arc length of the helix and divide that by the speed. But here we also have another method because we know theta dot, right? Theta dot can be solved as A length over R, taking the square root. Remember, theta dot is just d theta over dt. And as a result, so theta, this is equal to theta dot times t because of uniform speed. The parking garage has 5 storages, so therefore theta goes from 0 to 5 times 2 pi. 1 revolution is 2 pi. 5 revolution is 10 pi. T, this is just 10 pi over theta dot. Use the expression for theta dot. So therefore, this is 10 pi, 8 meters over 2.16, taking the square root. And that simplifies to 60.43 seconds. So it's a little bit over 1 minute to get from the bottom to the top. Okay, and that's it. Thanks for watching. We'll continue next time.